Previously, we have seen how the general tree search algorithm uses a strategy to determine which node on the fringe to explore next. An example of such a strategy was a first-in, first-out queue. We call this an uninformed search strategy because it does not use any information about the state itself. It only uses information about when the state was queued, but nothing that is internal to the state. We will now look at heuristic search strategies, which use information about the states on the fringe to determine which node to explore next. Information about a state that can be used in a search strategy can be encoded using a heuristic function. In general, a heuristic function h maps a node in the search space to a real number r. Or sometimes you also find that it maps it to a natural number. What a heuristic function encodes is the estimated cost of the cheapest path from the given node to a goal node. So the heuristic function tells us how close is the nearest goal node. Obviously, if the node n given to the heuristic function is a goal node, then the value must be 0. That is, we are already at a goal node, so the nearest goal node is in distance 0. As you can see, a heuristic function encodes problem-specific knowledge in a problem-independent way. For each problem we are looking at, we can define a different heuristic function, which is why the heuristic function is problem-specific. But whatever search space we're looking at, whatever problem we're looking at, the heuristic function will always give us a numeric value for each state. And the fact that it is a number is problem independent. A perfect heuristic function would always give us the correct distance to the nearest goal node. But if we had such a function, the search wouldn't be very hard. In fact, it would be trivial. Unfortunately, perfect heuristic functions are very hard to find for most of the problems we'll be looking at. Best first search is an instance of the general tree search algorithm, where we use the knowledge provided by the heuristic function to decide which of the nodes on the fringe looks best for expansion. In fact, best first search is a whole group of algorithms, as we can use the heuristic in various ways to decide which node looks best. And best first search can be used as a tree search or graph search algorithm, depending on whether we use the test for repeated nodes or not. In best first search, we use a strategy that uses an evaluation function f to decide which node in the state space to explore next. And again, the evaluation function maps a node in the state space to a real number r. In general, we will choose that node from the fringe which has the lowest value f. So the evaluation function determines the search strategy in best first search. Again, if we had a perfect evaluation function, we could use the search to lead us straight to the goal node. Note that the evaluation function is not problem-specific, it is specific to the algorithm. But the evaluation function may use the heuristic function, which is problem-specific. What we mean by best in best first search is simply defined by the evaluation function. The node that is best has the lowest f value. Now, a quick word about the implementation. There are really two operations that we need to support when we look at our fringe. When we generate the successors of a node, we need to add those to the fringe. And when we select a node from the fringe for expansion, we need to select the node with the lowest f value. Since we will do both of these operations quite often during the search, it is important that these are cheap operations. A good way to implement this is by means of a priority queue. A priority queue maintains all the nodes in the fringe in ascending order of their f values. A priority queue can be implemented as a binary tree, which means both adding a node and retrieving the node with the lowest f value has logarithmic time complexity. The simplest best first search algorithm is probably greedy best first search. This algorithm simply uses the heuristic function defined for the problem as the evaluation function used by the algorithm. Remember that the heuristic function is problem-specific and encodes the distance to the nearest goal node, whereas the evaluation function is not problem-specific and is used by the algorithm to determine which node to expand next. So the meaning of these two functions is really completely different. But greedy best first search simply equates the two and uses the heuristic function to give us a search strategy immediately. The result is an algorithm that always expands the node that is closest to the goal node next. The algorithm is called greedy because it always tries to take the largest chunk out of the remaining distance to the nearest goal node. It tries to get to the goal node in as few steps as possible. But since the number of steps isn't necessarily the cost of a path, this is not necessarily the optimal strategy. In fact, greedy best first search often gives us solutions that are far longer than the optimal path, and also far more costly. So let's look at our Turing-Romania problem to see how greedy best first search works. To remind you, the initial state was that we are in Arad. Now, suppose our goal state is to be in Bucharest, the capital. The actions we have available are to drive along the arcs shown in this graph. And each arc has an associated cost, and that is shown as a number next to the arc. So from Arad, I could drive to these three towns, and the costs would be respectively this, and this number. What we also need for greedy best first search is a heuristic, and that's what we've got here. The heuristic needs to estimate the distance to the nearest goal node, and our goal node is to be in Bucharest, so we only have one goal node. And on a map, we can use the straight line distance to estimate the distance to a different point on the map. So we will use the Euclidean distance between 2 points on a two-dimensional map. The table you are looking at simply gives us the values of our heuristic function for different nodes n. So if the node n is Arad, the distance would be 366, rounded. And so on. For each city in our map, we have a straight line distance in this table. And this is the value we will use as our heuristic value. As is to be expected, the heuristic value for the goal node is 0. Another feature of this heuristic is that it always underestimates the distance to the goal. Let's look at a simple example here. For example, we have Făgăraș, which according to the heuristic is 176 from the nearest goal node, Bucharest. But going back to the map, you can see that Făgăraș is really 211 from the goal node. That is because roads don't tend to be straight lines. In reality, it is probably something like this, and that's a longer distance than what the heuristic gives us. So the real distance is 211, but going to the next slide again, the estimated distance according to the heuristic is 176, which is lower. Another important observation here is that the heuristic presents us with additional information to what we had in the original problem description given by the map. There is no way you can compute the values in this table from the information given in the map. And of course, this table presents problem-specific information. Now, let us have a look at greedy best first search in action. What we see here is the initial state of the algorithm. All the nodes you see are the fringe nodes, and there's only one node, of course, initially. Fringe nodes are shown in blue here. That's the legend. And the node we select to expand next is shown in red. So currently there's no node selected. Within each node, you see the name of the city plus the heuristic value for that node. Also on the right-hand side, you see information about the depth of the different nodes in the search tree. So the first thing the algorithm does is select a node from the fringe. And since there is only one node, this is the one that's going to be selected. Then the algorithm performs the goal test on this node, which will fail in this case because this is not a goal node. The next step then is to generate the successors of this node. So now our initial state, Arad, is no longer on the fringe, but its three successors are now the new fringe. This means we have to go through another iteration of our loop, and the first step is to select a node from the fringe. We do this according to the strategy, which tells us we've got to select the node with the lowest f value. So here we have 3 nodes, and the lowest f value is this one. So this is the one we will select next. Again, this node does not pass the goal test, so we have to continue. We generate the successors and add these to the fringe. You can see what we are doing here is tree search because we've generated Arad again. So this node is the original node and we could go back there immediately. For most search problems, applying an action and then the reverse action immediately afterwards is not a good idea. But let's continue with the algorithm. So the next thing we have to do is select another node, and we select the node with the lowest f value, and here that is Fagaras. Again, this is not a goal node, so we have to expand it and add its two successors to the fringe. Now we select a node from the fringe, and the node with the lowest f value is Bucharest, and this time the goal test will pass. So we finished with our search. We can now extract the path to the goal node simply by going up from our goal node, the one that we found through the tree, to the initial state, and this is our solution path. That's it. That's how greedy best first search works.